So our third speaker is Maren Erven. Maren is a research assistant at Institute for Steel Construction and Materials Mechanics at TU Darmstadt, where she made her master's degree in 2018. Her research focuses on wire and arc additive manufacturing of steel nodes. She first came in touch with steel 3D printing in her master thesis, where she developed a new design for bolted head plates in steel construction. In 2019, she was part of AM Bridge team. During her studies, she gained experience in the building industry as engineer on site as well as in the office. So I will leave the screen to Maren to present design of optimized 3D printed steel node.
Okay. Hello, everybody. Can you hear me?
Yes.
Okay.
Please do
nice.
the presentation.
Thank you for that kind introduction. Oh, wait, I have to. Okay. No. I'm happy to be here today to talk to you and to such an audience of experts in the field of additive manufacturing in the built environment about my research in the field of additive manufacturing with steel. As already said, my presentation today has the title Design of Optimized 3D Printed Steel Nodes. So now let me give you a short overview about what you will hear in the next minutes. I will start with steel nodes and what is meant with that and why it seems useful to 3D print them with steel. And then, of course, I have to explain how these nodes will be printed and the additive manufacturing process planned therefore is WAAM. As I talk about optimized steel nodes, I will explain what is topology optimization and how I use it to find a structure to print. And the last point is what are the limitations come from all the points mentioned before the design has to deal with. And in the end, I will conclude everything, and I hope that you got an understanding of my idea of designing optimized 3D printed steel nodes. Oops. So let's start. The development of computer technology and the possibilities as it's opened up for engineering and above all the design of structures are leading to ever more spectacular buildings, especially when these structures are subject to high loads and wide spans are required, then steel is the material to choose. Sometimes it's no longer visible after completion of the building envelope, but it's still there. However, such structures require significantly higher construction and execution efforts. And this is mainly due to the nodes. Nodes here mean the connection of the linear elements, such as columns and beams. And the more demanding the overall structure is, appealing to architects, builders, and pedestrians, the more costly the design and the fabrication of the node becomes, so in essence for engineers and construction workers. And effort arises here in several forms. First of all, every structure, even if very low complex, like the second picture shows, contains different nodes which have to be designed. And moreover, architecture itself, we all know this, it's already subjected to high individuality. So every structure is different to each other. And furthermore, these nodes often more material is used than would actually have been necessary, since the saving of the material would only cause more waste and cost manufacturing time. Furthermore, in addition to the nodes, the connection components often have to be paired in a special way. So here, additive manufacturing has the potential to change things. So when we're looking at steel construction, we can see the nodes in different grades of complexity. And of course, I guess in grade 1, where the beams are just in a plane meet each other, then it isn't so interesting for 3D printing. But when it comes to stage 3, where all beams are coming from any direction with rotation and any kind of loads, then maybe 3D printing can help us. So how can it help us? I say with a few complex individual components, which are the 3D printed steel nodes, and many linear components, we can create a whole complex structure. And to get an advantage of the 3D printing, we can look for easy preparation of the linear components by using standard joints. So maybe in the end, we can think of a modular system with some individual nodes. So we get a remarkable, individual, awesome structure, but it doesn't matter which beam has to be placed in the end. And this also stands for reusability. So coming to the next point, how to print with steel, and when it comes to WAAM, and of course the use of in the construction industry, then I guess everybody knows this bridge from AMX3D, now placed in Amsterdam. Yeah, but I will go on and say, what is WAAM actually, and how does it work? So WAAM is actually just gas-treated metal arc welding, but unlike in the conventional way, where it connects two pieces, it creates the second piece layer by layer by layer. So, but yeah, we won't print plates. We will think of, yeah, structures, complex structures. As the name suggested it, the printing material here is the wire, and that makes it pretty fast compared to other 3D metal printing processes. So we can build up to 10 kilograms in an hour if you use multi-wire feeding systems. And what do we need to print? Yeah, if you don't want to print by hand, then we need a welding robot. And of course, we need a welding power source. And as it is wire arc additive manufacturing, we need wire. And as it uses gas-treated metal arc welding, we need the shielding gas. And these are the 4 basic components. And with that, you can print steel. Of course, there are some special power sources, there are special wires, special gases, special robots, and also additional things. But these 4 components are the crucial things, and that makes it cheap compared to other metal 3D printing processes. I said WAAM is fast, I said WAAM is cheap, and due to the fact that it's a process well known in the construction industry, yeah, I guess it's easy to invent. But it looks like it looks, so we have a rough surface where you can see the printing layers by eye. Anyway, I wouldn't say that doesn't matter, because if you need an even surface, then you can have some post-processing like milling. But a convincing advantage are the material properties. For WAAM carbon steel. With WAAM, we have a material which looks like normal hot rolled carbon steel. So we have a high Young's modulus, we have a distinctive yielding plateau, and we have a high plasticity. Everything what is needed for steel, we have it. But how to find the structures to print? And therefore, here short throw in for topology optimization, which is one kind of structural optimization. Yeah, we heard today different kinds of optimization, also form optimization. Here I use a topology optimization and especially the mathematical form of it. Here a structure is optimized by inserting holes where the material is not needed. And the aim of each optimization run is to find for a given mass that arrangement of elements with minimum compliance. For a given structural problem, like we can here see on the right, we want maybe find a stiffer structure for 50% of the mass, and the algorithm then says, okay, the red part is not as necessary as the green part is. But after that optimization, we don't know if the load can be transmitted anymore, so we have to do an additional analysis. And that leads me to the first limitations. The optimization, or the optimization I use, is can just think about linear problems. So that means we have no yielding, no buckling, and no nonlinear bearings. And here on the right, we can see what that means. Here are 3 results for the same mass restriction and actually the same load, but the second result has a significantly lower payload than the others have. But the algorithm would say, okay, they're actually equal to each other. That's because it doesn't focus on nonlinearities. Another problem is that for every optimization one, we have just one load case considered. So, but maybe our structure is in the end is subjected to different types of loading cases. We have this for structures which are placed on the outside. Wind will change our loads. So, and we can see that the results of the optimization run down here on this picture gives us different results. So sometimes we have to combine more results to have a valuable design. And the last thing is, when I say that optimization can just focus on linear problems, then it can just focus on the elastic material. But we see that for carbon steel, also the plastic behavior is crucial, and especially for 3D printed steel, we have here an anisotropy of the yield strength and the tensile strength. So we have to think about that. All of these limitations mostly need to be done in a post-processing. So we have our structure and result, and we have to analyze it in addition. The next limitations come with the printing process itself. Actually, we can print nearly anything. We can even print a bridge horizontally across water, as we showed in 2019. But some things are easier to print than others are, and a uniform printing process should be ensured. Therefore, the printing angle, which is the angle from vertical, should not vary too much. Because with different angles, we get a different behavior. You can see it on the right picture. So the behavior of the weld is different, and the layer height varies. At least parts of the structure should be worked in the same range. So we can split the structure into different parts, and these should behave in the same way. Next point is that we should avoid thin-walled structures because of the residual stresses inside the structure. And this comes along with the welding process. And here, a closed section is more stiff and will minimize the distortion because of that. And the last thing is that the distribution of materials should be consistent over the whole structure. And if we don't consider all of these points, then the printing process gets more difficult. And with that, the probability of process failures increases, and the probability of self-induced structure failures. And one last thing about limitations is, I said I want to facilitate the assembly later on. But if we don't think about the connection to the other components when designing it, then the optimization can give us the optimal result because it doesn't know the problem. So I would design the connecting parts with the design space. Here, for example, we can see flag plates and head plates. We can also think about other, maybe new connection, but I just have this example. But especially when we use connecting means like bolts, you can see it here, then we have to think about, we have to consider the assembly later on. So how will the bolts will be tightened? We have to have enough working space for the joining of the different components. To conclude everything, I have this example. That's a structure come out of one topology optimization run, but here the different types of limitations were considered. So the first thing we can see here is maybe here the small cross section, pretty small compared to the other ones. So we have no consistently distributed material at this place, and also here the structure will yield first when thinking about the nonlinear structural analysis. So we should enlarge that part. Next thing is, what about the assembly? In this node, every beam is printed directly to the node. So we should transport a part 5 times 5 times 5 meters to the construction site, or even just print everything in our workshop and then put the whole structure to the side. No, I don't think so. So we should think about connections. And so here's example. I just put in a hard plate and checked the space for the bolts. And the last thing, but it's not the only place in the structure, is we should avoid horizontal printing because we can't print in the air. Yeah, so that example is actually just what should be obtained when thinking about designing steel nodes 3D printed. And when we consider all that limitations, then maybe we can create a node that can change the design of structural steel frameworks, like I shown in the beginning of my presentation. Yeah, I have to thank these companies who support us with the crucial 4 basic components you need to print steel for our research in the additive manufacturing of steel. And I want to thank you for allowing me to speak to you today and for your attention. And I'm happy to hear your comments and questions.
Thank you, Maren. Great work. Thank you very much. So a quick question, how do you deal with the challenge of topology optimization, generating this complex form with a lot of thin pipes in the air, and then you have the constraint for FDM-based printing with your WAAM printer? Do you go back and regenerate the topology optimization, putting some obstacle on the way to regenerate those new bridges, or how do you actually deal with refining optimization based on fabrication constraint?
Yeah, actually the aim is to have an automatic process that focus on everything, but I'm not sure if I can do that. Until now, I can include some manufacturing restrictions into the optimization process, but it makes it a bit longer to calculate the structures, of course. So we can see, okay, I have just a printing angle around 40 degrees from the vertical. So the algorithm can think about that. And sometimes actually I just have more optimization results, which I combine. And to find the best of it, so a combination of all, and then yeah, do some manually additions.
So it's funny because like generative design of Autodesk, for instance, it's kind of, they don't call it optimization, but it's really combining in one way material reduction with manufacturing limitation. So as you choose your manufacturing setup, you generate generate form, optimal form based on those fabrication constraints. So I'm wondering if you would have in mind to integrate that into your algorithm for generating optimization in future.
Yeah, of course. I think about adopting other things to the algorithm or to the optimization process. Until now, I don't have like that algorithm. So yeah.
Yeah, thank you also from my side for this great presentation. Maybe I start with a comment. I think you could add one more aspect to the motivation of your research, that is a topic the entire day already, which goes beyond the creation of spectacular structures. It was interesting to see that I think almost all projects that you showed in the beginning are from the era before the big financial crisis of 2008, right? So there is a change, and in what quality of architecture is or might be. And as we experience today also in mass media and today in the discussions, there's another motivation to aim for what you are actually doing, reduce the consumption of material because of, yeah, well, you know, CO2 emissions, scarce resources, and so on. And I think in that sense, there's a lot to explore, and you explored a lot already in that sense to design and then material things that look different from the way they looked before, because they are produced in a much smarter way. So I think that is part of your work already. It was not expressed in the introduction, so that could be one more slide to put in. Anyway, the question for me would be, we heard Marina asking the question earlier today, how do we make these new technologies become dominant paradigms in the AEC? And one way to do that is disruptive, to say, well, we change everything. Now you're very strategic. You pick this one thing, which is the node, and say, that's the conventional construction, and then I'm changing this one thing that is a problem for conventional construction. And you just showed on your last slide the many companies you're working with, which hints also to the structure of construction industry, right? It's thousands of small companies. It's not the few big players. So it might be smart to have this strategy of gradually changing our industry. That's how I read your work. What are your experience when working with industry partners? Are they ready to make that transfer? Is it expensive? Do they just have to buy a robot and a little bit of gas and that's it, and then they could start? What are your thoughts on that?
Yeah, they're interested in that, but yeah, they don't want to do it. So I guess there has to be some examples for them, and if it works and if they see that it works, then they will use it. But okay, they're not there to now buy robots and begin printing, but they're interested in work, and I also get some node designs already, and they are interested if one can print them. So there's interesting, but I guess they're not brave enough.
Mm-hmm. Yeah.
Sorry.
May I also? Oh, so we have to move on, or? I mean, what I really enjoyed is the idea that you really, in the printing process, you integrate these existing plates, yeah, like the standard part that becomes the interface to the beams, which for me is a hint towards this idea of really optimizing also the printing speed, yeah, by just wherever you have something that you can take as a standard part and you integrate it into the printing process in a kind of conformal printing, yeah, you have the plates and you just weld in between kind of. I think that is very powerful. So I was wondering, you didn't really talk about the printing speed, but I guess WAAM is not the super fast process. So could you give us a hint about like how fast these prints are, and could you speculate a little bit if these prints are done in a prefabrication way, or more do you see the robot would be on site producing these nodes just in time during the assembly of the big beams?
Until now, I think of prefabrication, because when we have also this modular system, then it doesn't matter if it is printed on site, because then we can do it modularly in in the workshop where we can also have where we have a surrounding which yeah, has everything we need. On the construction side, there are some uncertainties and so on. So I would say print in the workshop, but maybe in the future, one can think about small little printing robots or steel print welding robots, which go to anywhere and just print on the structure. Also for yeah, or structures which crack or so on. Maybe we can think about small robots which repair the structure. But yeah, that's not my kind of research.
Thank you.